Unit 5 is by far my favorite unit for a couple different reasons. I like it first because it's really short. It's only 8 lessons. This is it. Like, I think our book, I think it has it in 11 lessons, maybe. Are there 11 lessons in this one? And just like we've been doing in some of our other ones, we get towards the end and we're like, you know, they go a little bit deeper than what we need. Yeah, there's only actually 11 lessons in the actual full unit. We're only going to do the first 8. Which means we're going to complete most of this entire unit next week. It's going to already be done, right, by the time we finish next week. So, holy cow. The other reason why I love Unit 5 is that it brings together some ideas we have seen throughout Unit 1 and Unit 2 and Unit 3 and Unit 4, and it pulls them together in a really great idea here. So that's part of what makes it so delightful. Some of this stuff is going to be very, very familiar. Here on our cover page, I want to give you kind of a sneak preview of the entire 8 lessons we're going to cover. Will you please write this on your Unit 5 cover page? And you might even just be wondering what Unit 5 is even titled or what it's all about. Because all of a sudden we just put a bunch of alphabet soup up here, right? Every letter that we've got going on. A's, C's, X's, H's, and K's. And what we're looking at is how we're going to do transformations of graphs. We're going to start transforming graphs to see how putting some different values in different places, A, C, H, and K, change what the graph looks like. Now I'm going to ask you not to write this next part, but I think that if I start making some connections with you, you're already going to be able to see that we've already looked at H and K many times over. So if you remember back to Unit 2, we were talking about polynomials. And if I think just about, let's see, something like x squared and what that graph looks like. Do you remember how it changed a value, how we started changing where the zeros were if we had something like x minus 2 squared? Do you remember how we could find the 0 of that function? When we were trying to turn factors into zeros. Emma, what do you remember?
Would it be 2? Because then it would cancel out and equal 0.
Nice. It would just be a positive 2 because then it would cancel out and be a 0 of the equation. So remember how we had something like x minus 2, and what it did is it moved that point that was at the origin, it moved it over 2 units to instead be right there. Do you remember in our polynomials unit what happened if we changed the constant at the end of a polynomial? Kennedy?
Was it like the y-intercept?
Nice, it changed that y-intercept. So it took the y-intercept that was here, and this one would move it up 7 units up to here. It still kept the same graph shape, it just changed where it was located. So we have already looked at things like h and k. The stuff that was inside with the x, that h value, is a horizontal translation. It slides it left and right. The k value is our constant. The thing that has no x's or y's or anything attached to it. Our constant does a vertical translation. That means it slides the graph up and down. So already we have seen a couple of these things take part and play out in some of our other values. We've also seen this with our horizontal and our vertical asymptotes when we were looking at rational functions. Remember how it started changing when our vertical asymptotes were in horizontal. We could draw some graphs and see where it changed. We also see this same idea happening with our exponential functions. When we start changing the multiplier in an exponential function, that multiplier, it changes the shape of our graph. And so we'll start looking at how that's going to change some values as well. So this is our starting point. We already have tackled what h and k are. We're just going to bring that back to the forefront and start looking at it, how it applies to all different kinds of graphs. Polynomials, radicals, rationals, exponents. Everything we've looked at so far. And then we're going to add in some more of these ideas of A and C that we have also looked at before too. All right, when we were talking about end behavior, if we had a negative leading coefficient, it flipped our graph over. That negative leading coefficient changed our end behavior. So if we had something that was up-down end behavior, it changed it so it was down-up end behavior. So we'll see what that's going to do for it. All right. So we want to think about how we have seen some of this before. In our lesson 1, we'll start to introduce some of our past ideas. Start with number 1, lesson 1 here. Take a look, jot down some ideas. What do you notice? What do you wonder? Be ready to share out some ideas. Maybe turn to someone next to you and see what they're writing down too. But be ready with a few things just from this very minimal graph. What do you notice? What do you wonder? All right. Let's see what some people have to say, what you're noticing and what you're wondering, and I'm just going to track some info that you say up here on the screen. Veronica, would you kick us off? What's something that you noticed or wondered about this graph?
I said it looks like a scatter plot.
All right, nice. Looks like something that we call a scatter plot. That's a great math vocab word. This idea that we don't have a drawn graph that's connecting it all together. We just have kind of some points that are scattered across our x and y coordinates going on here. So it looks like a scatter plot going on here, just kind of a bunch of data that we have. And that's really ultimately the goal of math, is to take some data, be able to write an equation to match it, And then we can use it to make all kinds of predictions and things about where this might go. So it looks like a scatter plot, and it might represent some kind of a data set. Taylor, what else did you notice or wonder about this graph?
I wonder what the temperature was in the clear spots, like for the hours that were happening.
Nice. All right. So Taylor's wondering, like, hey, that's a good thing to wonder about. What is the temp in this part? We have a couple places where it seems like somebody didn't collect some data in those giant spaces. And what could those be? Jacob, what's another thing that you noticed or wondered?
I said it was a decaying graph.
It was a decaying graph. Nice. This looks like it's got some kind of a decay going to it. So we know it's got definitely some kind of a downward slope to it. And the fact that you're using the word decay makes me also make the connection. You're probably thinking it's exponential decay. It's got a swoop or a curve to it. It's not a straight line. So it's this idea that buried in this sense that it's a decaying graph is that it's got a curve to it. It is not my calculators or my computer's having some kind of fun issues. Love it. I wonder if it's my cursor. I love technology sometimes. All right, it's a curve. It's not linear. That's what I'm trying to write there. It's some kind of a curve. It's something that is not aligned to it. There's definitely a curve happening here. Kay, did you notice or wonder anything else?
I noticed that there's like 3 different groups of dots.
All right, nice. Yeah, there's kind of 3 different groupings going on. This kind of pairs nicely with what Taylor said. The fact that we kind of have 3 groupings. We kind of have 3 separate groups of these dots that are going on. Maddie, did you have anything else that you noticed or wondered?
There's an outlier.
All right, there's an outlier. Which one would you think is the outlier?
Far down.
All right. This last guy, I love that you guys are bringing up lots of our information. That's good. This idea that it might be an outlier, this dot that's kind of all by itself. Now, an outlier means it's something that doesn't fit in with all the rest of our data. Something that looks very drastically different. And this one may be an outlier. If we're drawing a straight line to our graph, it's definitely an outlier. If we're looking at a curve to our graph, it may not be an outlier that we're seeing, but we have to see about what kind of graph fits our data, and then we can determine if that one is also part of it or not. So, let's see what this data is. We'll take care of section 1.2 and then we'll take our brain break for the day. So we've said some neat things about this warm-up that we've got. Let me capture that thinking real fast. Spectacular. And this is actually a data set that matches this situation in section 1.2. So that same scatter plot is now on section 1.2 on our graph. But they've given us a couple actual graphs to match along with it. So here's the situation behind this data that they collected. A bottle of soda water is left outside on a cold day. The scatter plot shows the temperature in degrees Fahrenheit of the bottle hours after it was left outside. There are 2 functions that they gave us to model these 2. Let's put names to what these are because we've seen these in our past. Our first one, our f of h, is a rational function. I know it's rational because it's got a ratio in it. It has a fraction. When we looked at these previously, we were using rational functions to set horizontal and vertical asymptotes. So if you remember, this was when we were having things like, we were ordering t-shirts and we were finding the cost per shirt depending on how many shirts we bought. Or we were looking at a current in a river, and if the current was going too fast, our boat would never get to where we were going. So distance, rate, and time. Our rational function tells us some things like 45 being our horizontal asymptote. So as our f function continues to move forward more and more, it's going to get closer and closer to that horizontal line at 45. And we have a vertical asymptote based on the denominator over a fraction. Remember how a denominator can't equal 0? So this is going to tell us our vertical asymptote at negative 0.5. Something just on the other side of our x-axis right there. Our y-axis, I'm sorry. On the other side of our y-axis. Our other function looks a lot like our exponentials that we just talked about in Unit 4. It's showing exponential decay going on, so using that idea that I think Jacob gave us, that idea that we're showing a decaying graph. This has a growth factor that is cutting in half every certain amount of timeline that we have going on, right? So we have our growth factor here. So the big ultimate question, which function fits the graph better? They both have a 45 in them. They both have this starting idea that we're beginning at 45, or somehow that's going to be our horizontal asymptote. That's what we're getting closer and closer to for each of them. Talk with the person next to you. Decide which one you think fits better and why you would justify that thought. There's someone either at your elbow or in front of or behind you. Talk with them first. Have a debate and decide which one of these two fits better and why. Alyssa, what'd you guys say? Which one seems to fit better? Ooh, why am I helping you? Big. I love technology. I really do. All right, sorry. Which one did you guys say fits better? There's no right or wrong here. Which of those two lines, the F graph, does it seem to fit more of the data points, or the G graph? Which one seems to be closer to more of the data?
The top one.
The top one, you like the F graph better?
Oh, it's the top one. I don't know which one it is.
Yeah. So that top one that we see there, I see it's paired up here with the F function, so I'm guessing that this top one looks like the F graph going on here. That top one, maybe the F function seems to fit better. What makes you think that the top one seems to fit better? Alright, close for more data. Taylor, what are you thinking?
I was gonna say the same thing. I was gonna say that there's 5 closer to the, like, to the G.
Okay.
And there's 6 on the other side of the F.
Alright, so Taylor's going by a count of all of these numbers, right? We have 5 of them that seem to be kind of closer to the G one here. And then we have these 6 guys that are closer to the F1, definitely, because they're even above that F1, nowhere near, I don't want to say nowhere near, but less close to the G. And then we've got this kind of last little guy that's kind of in the middle there. Yeah, Jacob, what would you say?
I said G because it kind of looks like the F on the left. It keeps going up.
Alright, so G, you're saying G looks more like it because on the left it keeps on.
F keeps on going up and it's
Gotcha.
decrease.
Alright, so we could also say that G looks better because the F function, it seems to keep on going up and up and up, like it's almost got that asymptote, so it's going to keep going to some higher data. Where our data seems to start right here at this point and move from there. So G, because at the left side, it seems to have like an ending point. Alright. So we could start to see that we can make an argument for either one of these. There are different ways to model the same amounts of data. And our goal in math is to always find the one that matches the best. So we're going to start seeing throughout this unit how we can take some data points and how we can adjust a graph. We can move it up or down. We can slide it left and right. We can start to stretch it. We can start to squishy it and make it shorter. We're going to do whatever we need to match what the data tells us it needs to be. If we could take this F graph and maybe kind of like tip it a little bit, do you see that it would probably pick up some more of our data a little bit better? If we could kind of change that angle so it would catch more of these points up here while still also kind of catching more of these points in the middle, we could have a nice looking graph that would better match. Or if we took the entire G graph and slid it up just a little bit, it might also match more of our data points a little bit better. So we're going to start seeing how we can adjust that to match. All right, let's take a 5-minute stretch break. Stand up, get a drink of water. If I can bring you back together, you may still have one more graph that you're working on, but it seems like most of our groups and partnerships are all done with all of theirs. Thank you for that. I heard some fantastic conversations. I heard some people who said, oh, you told me to slide it, but you didn't tell me left or right. I heard someone say, oh, you're just going to flip it over. And so they redrew their graph and they're like, oh wait, I meant flip it over this way, right, left and right, not flip it over upside down. And so we want to always just be very specific as we're making these descriptions about how far we're moving something, which direction we're moving it, left and right, up and down, and which direction we're also flipping it or reflecting it, which I heard some great people using some awesome geometry terms. And you're reflecting, or somebody said, ooh, rotate it. They didn't even use to reflect that one. They're like, ooh, just rotate it 90 degrees from that y-intercept. And I was like, oh, what a smart way to describe that one. There's some great ways to do it. So there are multiple ways we can describe these graph changes. But being able to use our words is the important idea for our starting point here, so we're very specific about which direction and how far. While you guys were working, I passed out hopefully 4 packets of paper to you. Will you double check with me that you have all 4 of those? Your first one should be the Unit 4 test review. You should have then a Unit 5 cool down packet. You should also have a Unit 6 cool down packet. It's got a big circle on the front of it. So the Unit 6 student packet, big circle. And then your Unit 7 cool down student packet. Did I skip? What did I miss?
I need the 6 and 7.
6 and 7. All right. Anyone else that I missed on any of those 4 items? Awesome. All right. Now, I don't mean to flood you with paper, but I just want to make sure. I don't know about you, but I'm incredibly nervous about next week. So, if you just have everything that we might need on paper with you now, whatever happens, we are just ready for it and good to go. All right, so I wanted to make sure you had everything that you're going to need. That's for the whole rest of the year, for our next 8 weeks. Okay? So while you have that, let's take a look at the Lesson 1 cool down in our Unit 5 packet. Will you find your Unit 5 cool down packet and look at number 1 with me, lesson number 1. And our lesson 1 cool down is just asking you to find at least 2 ways to move this graph so it goes through this point at 1, 2. There are lots of ways to do it. I'd like you to just describe 2 of them. Give you a chance to do that. We're going to share and compare in just about 2 minutes or so. Alrighty. So we're taking a look here at the cool down from lesson 1 after we looked at how we could describe some changes in the graph. This was a partner activity that we did in class. And so I saw in my sample one here that we ended up squishing it so that it was skinnier. And we did it so that it was actually half as wide as what we started with. That was our idea here. So we took something that only had 2 top points like this, and we made it have 4 top points up here. So that was kind of our idea for this one. Now for a cool down, to match this up together, we did this in class, I just forgot to record it. How many ways we can translate this curved graph so it goes through point 1, 2 like this. And there were lots of different ways that students identified how to do it. One way that a student identified was to take this whole graph and to move it up 1 unit and then to the right 1 unit. Up 1 and to the right 1. The big idea is that we're trying to be specific about which direction we're moving it and how far. So by moving that graph up 1 unit and to the right 1, it would take this curved line, that's not traced very nicely, and it would move it up 1 unit and then to the right 1 unit, and it would look just like that. Now another way that a second student gave us for how we could change this up was to just slide it to the right 2 units. So that would take this graph, this time in red, and sliding every single point 2 units to the right would move that graph here to go through that point. And another student came up with the idea that we could reflect it over the y-axis. It's a perfect way to describe it, because I would take our graph here and reflect it so that this point gets reflected over here. Every single point would get reflected. And so we'd end up with a graph that looks kind of like this. So we could have something that reflects it over the y-axis. There are lots of other ways. We could also just slide it straight up 1.5 units. That would also get us to that point that we're looking for. So lots of ways we could go about doing this. All right, you are ready to tackle the lesson 1 practice problems. Give it your best shot. Thanks, friends.